I'm R. Prabha, Assistant Professor in the Department of ECE, SNS College of Technology. In this video, we will see the topic on wave equations for the course Electromagnetic Fields and Waves. So, before going to derive the wave equation, we should know about uniform plane waves. An electromagnetic wave originates from a point in free space spread out uniformly in all directions and it forms a spherical wavefront. An observer at a larger distance from the source is able to observe only a small part of the wave, and the wave appears to him as a plane wave. So, for such a wave, the electric field E vector and the magnetic field H vector are perpendicular to each other and also perpendicular to the direction of propagation. So, we can conclude that a uniform plane wave is one in which electric field and magnetic field lie in a plane and have the same value everywhere in that plane at any fixed instant. And a uniform plane wave traveling in z direction, the space variation of electric field and magnetic field are zero over a constant z plane. And this implies that the fields have neither x or y dependence, that is the differentiation with respect to x and y is equal to 0, that is dou by dou x and dou by dou y is equal to 0. And a plane wave is transverse in nature, that is electric and magnetic field are both perpendicular to the direction of propagation. So they are called as transverse electromagnetic waves, simply called as TEM waves. And this is the picture of a plane wave. So here the wave of this type have electric and magnetic field are entirely transferred to the direction of propagation, are perpendicular to the direction of propagation, and they are called as transverse electromagnetic wave. And for deriving the wave equation for uniform plane waves, assuming a plane wave is traveling in the direction of x-axis, the electric field E has only the component of Ey in the y direction, and the magnetic field H only have a component of Hz in the z direction. It is said that this wave is polarized in the y direction, that is vertically polarized, because the electric field vector is in y direction. And since we are dealing with a non-conducting medium, the conduction current density J is equal to 0. So the Maxwell's equation derived from Ampere's law reduces to del cross H is equal to dou D by dou T. And we are representing this in rectangular coordinates, that is dou Hy by dou y minus dou Hy by dou y plus y vector into dou Hy by dou z minus dou Hy by dou x plus z vector into dou Hy by dou x minus dou Hy by dou y is equal to dou by dou z of x vector dz plus y vector dz plus z vector dz. And for a plane wave traveling in the x direction, the only component of equation above that combines are minus y vector into dou Hy by dou x is equal to y vector into dou dy by dou t. And we can write dou Hy by dou y is equal to minus epsilon dou Ey by dou t, because the unit vectors y vectors cancelled at both sides, and we know the relationship between displacement density vector and the electric field is d is equal to epsilon e. So that we can write the equation dou Hy by dou x equal to minus epsilon dou Ey by dou t, and this epsilon is called the permittivity of the medium. And another equation, Maxwell's another equation derived from Faraday's law is del cross E is equal to minus dou B by dou t. And so we can also writing this in rectangular coordinates as x cap dou E y by dou y minus dou E y by dou z plus y vector into dou E z by dou x plus minus dou E y by dou z plus z vector into dou E y by dou x minus dou E z by dou y is equal to minus dou by dou t of x vector dx vector plus y vector dy vector plus z vector by vector. So by comparing these two, we can write the component of z. Because the plane wave is traveling in x direction, it has only the contribution is z vector into dou e y by dou x is equal to minus z vector into dou e z by dou t. So we can write this as dou e y by dou x equal to minus mu into dou h z by dou t, because we know that h is equal b is equal to mu h. And by comparing the equation 4, the space derivative of hy to the time derivative of ey. And similarly, the equation 8 relates the space derivative of ey to the time derivative of hy. So differentiating equation 4 with respect to time t and 8 with respect to distance x, hz can be eliminated and an expression obtained for ey in terms of y and x. And proceeding in the similar way, from equation 4 we can write dou by dou t of dou h z by dou x equal to minus epsilon dou square dy by dou t square, or we can write dou square dy by dou x square is equal to minus mu dou h y by dou x dou t. And similarly, dividing by equation 10, it gives minus 1 by mu dou square dy by dou x squared is equal to dou by dou x of dou h y by dou t. So this is obtained by dividing equation 10 by minus mu. And if, this equation does not matter whether we differentiate first with respect to x and then with respect to t, or vice versa. The left hand side of equation 9 is equal to the right hand side of equation 11. So finally we can conclude that dou squared ey by dou t squared is equal to 1 by mu epsilon dou squared ey by dou x squared. So this is equation number 12. This relates the space and time variation of the scalar magnitude of Ey of the electric field intensity and is called a wave equation in terms of Ey. It is in fact a scalar wave equation of the simplest form. And now differentiating equation 4 and 8 in reverse order, that is equation 4 is differentiated with respect to x and equation 8 is differentiated with respect to t. We can eliminate Ey and obtain another wave equation in terms of hy as dou squared hy by dou t squared is equal to 1 by mu epsilon dou squared hy dou x squared. So both these equation number 12 and 13 are the same form. A wave equation given by 12 and 13 has many important physical applications, and they are also called as D'Alembert's equation. And now there are some important consideration of uniform plane waves, that is the velocity squaring the velocities is equal to 1 by mu epsilon, that is v squared is equal to 1 by mu epsilon. And dou squared ey by dou x squared can be written as v squared into dou squared ey by dou x squared. And dimensionality we are obtaining v is equal to meters per second, because volts per meter second squared is equal to v squared into volts per meter cube. So v is equal to meters per second. So this is the dimensions of velocity. This velocity is a characteristics of the medium being dependent of the constant mu and epsilon of the medium. For free space, and v is approximately equal to 300 meters per second. And a uniform plane wave is a very idealized case. It can adequately model many practical situations in wireless communications, radar, etc. For example, fields impinging on receiving antennas that are far away from transmitting antennas are practically uniform plane waves. So the properties of uniform plane waves, we have seen the properties, and Alembert's wave equation we have derived, and the uniform plane wave application also we have seen. Thank you.